All right, we previously described what the P wave looks like. Let's look at it now in the context of the whole story. Let's apply our simple two-lead system, where we're going to put our negative lead here and our positive lead here. And what we just watched was the dipole, or the series of dipoles really, that was formed as the electrical conduction passed from the SA node to the AV node. And that gave us our P wave. Now, we see this gap right here where things have slowed down, right? Not a whole lot's happening because, again, that's the purpose of the SA node. Sometimes we'll see that gap elongated right before we really start our QRS complex. If that gap's elongated, we know there's something weird going on with the AV node. It's slowing it down too much. There's some sort of block there. Now, the QRS complex is a little bit more complicated because we've got some negative deflection, then we got a strong positive deflection, then we go back to a negative deflection. Let's see if we can highlight those dipoles on our picture of the heart. So as we've gone through the bundle of His, what are we going to see now? We're right at this point, and we're going to divide. We're going to go this way, and we're going to go this way. As these signals then spread down the bundle branches, we see a very, very strong dipole develop, where these cells on this side, on the left side, depolarize first, so we have negatives over here. But over on the other side, we haven't quite got that far down, so we still have positives over here. And this creates a very, very strong dipole. If we draw our dipole again from negative to positive, that looks like that. Now, remembering the rules that we talked about, what does that look like in relation to the lead axis? Let's draw our lead axis, and we can see, thinking again of vector math, if we draw our perpendicular axis, the parallel component of this dipole arrow is right there. And it is going toward the negative lead. So because this arrow, this dipole arrow, has a bias toward the negative lead, it gives us a negative deflection. This is my Q wave right here. Negative as the signal travels down the bundle branches. Of course, the next stop, once we're past the bundle branches, is the Purkinje fibers. And what we see with the Purkinje fibers, vectors outward in this direction. And you can see that the vast majority of those are becoming a lot more parallel to the lead axis, and they're pointing to the positive lead. And so this is where we see the R peak, right? My maximum positive deflection as the apex of the heart begins to fire, and as that transmits from the inside to the outside through those Purkinje fibers. And by inside, I mean endocardium to the outside, the epicardium, the pericardial space. That's the direction that the conduction takes along the Purkinje fibers. And then as we follow these fibers, you can see we're starting to become parallel again, perpendicular with my lead axis. Right there, I'm really perpendicular. Where am I? I'm kind of back over here at baseline. But my last little bit, we can do this on the right side too. My last little bit, these vectors are pointing toward the negative lead. And it's that last bit of the Purkinje fibers firing that gives me the S component of my QRS complex. And then, once they've all fired and they've all depolarized, where do I go? I go back to baseline, and that's the end of ventricular depolarization. All right, now we want to understand the T wave. And previously we defined this as ventricular repolarization. This is where it gets a little bit interesting. So let's do this. Let's take this area right here, and let's zoom in and see what this might look like. We're looking specifically at the Purkinje fibers. Okay, here's a series of cells making up those Purkinje fibers. Let's orient ourselves. This was kind of the inside of the heart, the endocardial area, and this was going to be the outside. And as we showed before, the direction of depolarization was in to out. let's show what that might look like in charges. Of course, before any of this happened, we're positive on the outside, negative on the inside. And the first one to flip is going to be the one on the inside. So this one flips. We're negative on the outside, positive on the inside. We go through the process. We're looking at our dipole arrow. We draw our dipole arrow toward the positive end of the dipole. If you remember where our leads were, this is going to be a positive deflection because our leads were essentially positive over here and negative over here. Okay, let's go through the entire process and let's depolarize all of these cells. Now we're positive on the inside, negative on the outside. Take just a second and think, okay, what's going to happen next? How am I going to repolarize? Remember, we started here. All things equal, then that should be the one that would repolarize. So let's do that. Let's depolarize this cell, meaning we're going to take our positive ions back out because potassium's leaving the cell, and that's going to leave a negative on the inside. What would this look like on an EKG? Well, there's our dipole right there. We draw our dipole arrow pointing to the positive end of that dipole, and lo and behold, that arrow is pointed to the negative lead. This should be a negative deflection. But if you recall from the EKG, what did it look like? The T wave was actually a positive deflection. What did we miss? Let's go back to where we left off. And now we have to recognize that even though the direction of depolarization started here, the direction of repolarization doesn't have to go in the same direction. What if the last one to depolarize was actually the first one to repolarize? So let's come here at the end and let's flip them. There we go. It just changed back. Our direction now is out to in from your screen right to left. If we look at our dipole, there it is. So we draw our dipole arrow pointed to the positive end of our dipole. It's pointed to the positive lead. We have a positive deflection. So the next one to flip is going to be this one, and so forth. We see the direction now going from out to in the repolarization event. Now, it's actually not uncommon to find people that have an inverted T wave, but more often than not, that's actually diagnostic for something like ischemia, where following a heart attack or something, that part of the heart is actually damaged and these cells are out of sync, and so the timing of the cells becomes equal. And when we saw that, if all the timing of each cell is equal, then the direction of depolarization would be the same direction of repolarization, and we would see an inverted T wave or a negatively defected T wave. I do want to just make one next comment. What's regulating this? This is a nice review. How could this one over here, the cell on the far right, have such a short event? It's the last one to depolarize and the first one to repolarize. That means that the one over here at the start, this one over here, this one has to have a very, very long depolarizing event. I want you to think for just a second what that might look like. Remember, in our cardiomyocyte action potential, if we were to graph this out, we're down here at resting membrane potential, really negative, minus 70. We have the quick and rapid upswing. Then we have this plateau phase. And then we're back down. And remember, this plateau phase is all about L-type calcium channels. And it's designed to increase calcium permeability, the length of permeability, how much calcium gets in, and the more calcium gets in, the stronger the contraction, right? Well, we can see, if we were to label these, cell A versus the end one out here, cell E, how are they going to be different when we're looking at this cardiac action potential? I hope you can appreciate that cell E, the action potential could look something like this. We're still negative. We have the same kind of process, but our plateau phase just isn't nearly as long because of how those L-type calcium channels are regulated. And it's the timing of those L-type calcium channels that allows for the repolarization of the QRS complex to be a positive deflection instead of a negative deflection. Now, you might be asking, well, what about the P wave? Why don't I see the deflection there? Well, this would be a true opposite deflection. In other words, this would be a negative deflection, but we don't see it in the graph simply because if we go back and look back up at the graph, it's hidden in this massive QRX complex. It's there, but because the QRS complex is so dominant, there's just no way we're going to be able to see it with the lead system that we have. It's buried inside of this. All right, so in summary, as we've looked at the electrical conduction pathways of the heart, we identify the P wave as a positive deflection of atrial contraction, as the electrical conduction travels from the SA node to the AV node. Then there's a space given to us by the AV node where everything slows down so that now we can wait for the actual physical contraction to happen, right? The electrical stimulus happens first, and then the cells actually do their thing. Okay, now we've delayed. We get across the bundle of His. We enter our bundle branches. This is where we see the QRS complex. As the signal travels rapidly down my bundle branches, that's what Q is traveling down the bundle branches. Once we hit the apex of the heart, now we start spreading through the Purkinje fibers, and recognize this is where the contraction of the ventricles begins, at the apex, as we then start to squeeze upward. So R represents maximal deflection when the apex of the heart is contracting, and then as this electrical conduction spreads laterally and toward the top of the heart, this is where we start to see the S wave, which represents the final element of ventricular contraction. Then there's a delay, and then we see ventricular repolarization with a T wave. The reason the T wave is a positive deflection is because the direction of depolarization is actually the opposite of the direction of repolarization. And hopefully that gives you a good idea now of what the basis for the EKG is.